All right, so let's take a deeper look into these bicyclic compounds. So again, here we're going to have our cyclopentadiene, and in this case, it's going to react with our dienophile, which we're just going to put two aldehydes here, cis to one another. And so we can have one of two products here where our carbonyls here are either both pointing up or they're both pointing down. And so we're going to draw the three-dimensional representation of this. So we draw our cyclohexane, put that bridge head there, that double bond there, and then we'll put both of these carbonyls pointing up in this case, and then we can draw another product in which they're both pointing down. Right? See the difference between pointing up and pointing down. And so when we have them pointing up, and it's really that they're away or that they're anti to the larger component of the bridge, right? This component of the bridge has 1, 2, whereas this one only has 1. And so they're on the opposite side of the large component of the bridge. We call this exo. And so we go say anti to the larger bridge. And then the other situation we can have is now these two components are closer to the larger bridge or cis to the larger bridge or syn to the larger bridge, and we call this endo. And so Diels-Alder reactions will almost always prefer the endo product. The endo is always, almost always preferred. And so if you think about the sterics of this, you'd actually kind of want the big thing closer to the smaller bridgehead, right? Because that's less sterically hindered. And so why does it prefer the kind of more sterically hindered state? And it has to do with the transition state of the compound. And the overall kind of reasoning here is that it gets complicated, but basically that the orbitals of the electron withdrawing group overlap the pi orbitals of the diene in the endo transition state. And so this overlap of these electron withdrawing groups and the diene make the transition state lower in energy, which causes this to be the major product. And so I'm not going to try to draw this, but I have a picture. So on the top is the endo transition state. And so we can see, even though it's more sterically cluttered, we have these electron withdrawing groups right next to our diene, whereas in the exo transition state, the electron withdrawing groups are not really close to our diene, which makes them go, makes them higher in energy, which makes it less likely to happen, right? And so this is a stabilization interaction. Right, stabilizing interaction, which makes this go faster, which results in the endo being the major product and oftentimes the only product. And so if we drew the product here between the cyclopentadiene and this maleic anhydride, think about what it would look like, right? We're going to draw our cyclohexane with our bridgehead and then the pi bond, and they're both going to be in the endo position. So both of these components are going to go down. We'll have carbonyls on either end, and then fuse them together with this oxygen. And so this is the major and oftentimes the only product. And then if we draw the product for the exo, again, draw your cyclohexane with the bridgehead and then the pi bond. And now in this case, they're both pointing up, right, with our carbonyls, and then our oxygen bridging those two. I won't ask you about the kind of transition state type of questions, but you do need to be able to identify the difference between endo and exo, be able to draw the product, and tell me which one is preferred.